I never knew you worked on a Mars rover for NASA, and that revelation always sparks the same reaction: amazement. What makes it even more surreal is how my name, Mark Rober, is only 2 letters away from Mars Rover. Swap the K for an S and the B for AV, and suddenly it feels almost prophetic. Strangely, it took me about 4 years working at NASA before that realization hit me. One random day, the connection clicked, and I just thought, oh, dang, that's wild. Sometimes the most obvious coincidences take the longest to notice, especially when you're deeply focused on the work itself rather than the poetry surrounding it. By training, I'm a mechanical engineer. I earned both my bachelor's and master's degrees in that field, which laid the foundation for what came next. I ended up working on a Mars rover mission for about 7 years, which still feels unreal to say out loud. NASA has a unique way of onboarding engineers. They essentially throw you into the deep end. You're given responsibility over a real piece of hardware that's going to space, and you're expected to figure out, learn fast, and ask the right questions before something very expensive goes very wrong. In my case, I was responsible for a specific section of the rover. That meant designing how it should look, testing it under extreme conditions, integrating it with other systems, and overseeing how it all came together. You're never working alone, though. There's a whole team involved, plus senior engineers who review your work. At NASA, they jokingly call these reviewers the graybeards. Their job is to look at your design and explain in detail all the ways it could fail. You take their feedback, revise everything, and come back stronger. The process can feel intimidating, almost mythic. It's like trekking up a mountain to seek wisdom from someone who has seen everything go wrong before. But those people earn their authority. They put hardware into space successfully, and they know the consequences of missing even a small detail. NASA intentionally gives young engineers big responsibilities, but they surround them with experience. That balance of trust and scrutiny is what keeps missions alive. You learn quickly that criticism isn't personal. It's a survival tool when failure isn't an option. I was specifically in charge of a trunk-like component on top of the rover. The robotic arm digs into Martian soil, collects a sample, and then deposits it into the rover's body. I designed the hardware that receives that sample. The fact that it's still functioning on Mars today is something I think about often. When you look up at the night sky and spot that faint red, there's a strange comfort in knowing exactly where your baby is. Even though it's 90 million miles away, that distance never stops feeling absurd. I've physically touched and assembled something that's currently rolling around on a tiny red speck in the sky. What makes it even more mind-bending is thinking about time. On Earth, everything oxidizes, metal rusts, structures crumble, and eventually nature claims everything. If humanity vanished 1,000,000 years from now, there would be almost no trace of us left. Earth would quietly erase our presence, returning to forests, oceans, and stone. Mars is different. There's no oxygen in the same way. So things don't break down. 1,000,000 years from now, those rovers will likely still be sitting there, frozen in time. If some alien civilization visited Earth and Mars, they'd see a lush, untouched planet here and strange machines on Mars. They'd wonder where those objects came from. That idea alone makes the work feel eternal, in a way few human projects ever are. Our fingerprints might last longer on Mars than on our own planet. Working in space teaches you unexpected lessons, especially about physics. One of the most fascinating things is the absence of air resistance. Once you leave Earth's atmosphere, you don't need constant thrust. You accelerate at the beginning, reaching around 20 to 25,000 miles per hour, which is several times faster than a bullet. After that, you coast. For months, you're essentially drifting through space, aiming not for where Mars is, but where it will be when you arrive. During that journey, you only get a few chances to make course corrections. The thrusters used for those adjustments are incredibly small. We jokingly call them mouse fart motors because the tiniest puff can change everything. When you're traveling tens of millions of miles, a fraction of a degree off can mean missing planet entirely. A subtle nudge at the right moment is enough to ensure you arrive exactly where Mars will be months later. Orbital mechanics sounds impossibly complex, but the lack of friction actually simplifies the math. Computers handle most of it with ease. Over time, engineers also learned to use gravitational slingshots, where spacecraft gain speed by looping around planets. It's like swinging around a pole to go faster without using extra energy. Still, the scale is hard to comprehend. Landing something on Mars is like hitting a golf ball in New York City and getting a hole-in-one in Los Angeles. Science fiction often captures this sense of scale beautifully. One book that stands out is Seven Eves by Neil Stephenson. The very first line states, "The moon exploded," and that hook pulls you in immediately. The novel dives deep into orbital dynamics as humanity repurposes the International Space Station into a survival habitat. Because Stevenson writes hard science fiction, much of the technical detail is grounded in real physics, making it both educational and thrilling. In the story, the moon breaks into 7 pieces, which then begin colliding and multiplying into more fragments. Eventually, this creates a catastrophic hard rain of debris that renders Earth uninhabitable for thousands of years. Humanity has only a limited time to escape. Alongside the science, the book explores politics, power, and moral dilemmas. Who gets to leave Earth? What laws apply in space? Even defining crime becomes complicated when prisons don't exist beyond the atmosphere. Those ideas aren't purely fictional. Space junk is a real and growing problem. If 2 satellites collide, they can generate thousands of debris fragments, each one dangerous. Those fragments can trigger further collisions, creating a runaway chain reaction. That's why we track every object larger than roughly a golf ball orbiting Earth. There's no cosmic vacuum cleaner to clean it all up, at least not yet. But engineers are actively working on missions designed to remove defunct satellites. Anytime you launch something into orbit now, you must have a deorbit plan. I recently helped build a satellite that lets people upload photos, which appear on a screen in space. A camera then takes a picture of that display, giving you a literal selfie in orbit. It was designed as a free outreach project to excite kids about science. Even with something playful like that, regulations require that after about 5 years, the satellite must safely burn up in Earth's atmosphere. That requirement is a lot like entering a country on a visa and being asked when you plan to leave. Space agencies want assurance that your hardware won't become permanent junk. Deorbiting works because once an object dips low enough, atmospheric drag increases. Friction heats it up until it disintegrates completely. Almost nothing survives the descent. It's a controlled ending built into mission from the start, and it reflects how seriously space sustainability is taken today. Another surprising area I learned about is astropolitics. Who owns the moon? Who owns an asteroid? Does a country own the space directly above its borders? And if so, how far does that ownership extend? What happens if someone captures an asteroid rich in lithium or gold and suddenly doubles Earth's supply? Entire economic models are based on scarcity within a closed system, introduce massive new resources, and the math underpinning global markets starts to break. This is where emerging technologies like AI make things even more unpredictable. Many of the rules we relied on for centuries may no longer apply. History shows that major technological shifts are painful before they're stabilizing. The move from agriculture to the Industrial Revolution displaced millions of people. Entire professions disappeared, including unexpected ones that supported the old system. Today's shift could be even bigger, because machines aren't just replacing manual labor, they're beginning to replace cognitive work as well. Through all of this, my time at NASA permanently rewired how I approach projects. One of the biggest lessons is the power of prototyping. People often try to build the final version first, aiming for perfection right away. That's almost always a mistake. At NASA, you build quick, ugly prototypes. You build several. You test them, tweak them, and intentionally break them to understand their limits. Only after learning everything possible do you attempt the final version. That philosophy carried directly into my YouTube work and my broader life. Failure isn't something to avoid. It's the goal. You want to find out what doesn't work as quickly as possible. Whether it's designing Rover wheels or building a robotic goalie that can block soccer shots, there are countless failed versions before success. Each failure provides data. Over time, you stop fearing mistakes and start seeing them as progress indicators, Proof that you're pushing boundaries instead of standing still.